behind all tests of significance. First, we will assume that nothing is going on. For me, the analogy to our legal system helps make the process clearer. When a person is convicted of a crime, the jury is instructed to assume the person is innocent and to keep holding on to this assumption while they listen to the evidence. When all the evidence is presented, the jury must then decide whether the evidence is strong enough to reject the assumption of innocence. Otherwise, they will fail to convict. Keep in mind that when juries fail to convict a person, this is very different from deciding the person is innocent. They simply cannot, based on the evidence, say without a reasonable doubt that the person is guilty as charged. So in statistics, we start out by assuming that nothing unusual is going on, analogous to assuming someone is innocent. Then we consider the data. That's our evidence. We find out how likely it is that our result could have occurred purely by chance. If the result is very unlikely or surprising, we have reason to believe that something is going on. We measure how likely or surprising a result is by something called a p-value, and we're going to learn how p-values are determined. So let's get specific about how to conduct a test of significance. Here's an example. In the 1960s, about 44% of the population had never smoked cigarettes. 35 years later, in 1995, data was collected on 881 adults, and it showed that in this sample, 52% of the adults had never smoked. The sample suggests that the percent who never smoke rose during that 35-year period. There certainly was a lot of research during that time that confirmed the tremendous health risks for smokers, and a lot of media attention was given to these health risks. So was the data collected in 1995 strong enough to conclude that the percent of non-smokers had in fact increased? Or could it be due just to chance fluctuations? In a test of significance, the assumption that nothing is going on is called the null hypothesis and is written H subscript 0. In this study, the null hypothesis says that there is no change in the percent of non-smokers, and that the percent in 1995 is the same as it was in the 1960s, namely 44%. It is important to recognize the general form of a null hypothesis. It says that a parameter is equal to some hypothesized value. In this case, it says that the true proportion of non-smokers in 1995 is still 44%. Nothing has changed since the 1960s. We also need to create an alternative hypothesis, which formally states that something is going on. It is called, logically enough, the alternative hypothesis, and is written H subscript A. So, in a test of significance, we compare data collected during an experiment to what we would expect to observe if there was no effect. This comparison gives us evidence either for or against the null hypothesis. Both the null and alternative hypothesis need to be expressed numerically. In this study, the null hypothesis states that the population proportion of non-smokers in 1995 is 44%, and the reasonable alternative is that it has increased and is now greater than 44%. Notice the null and alternative hypothesis are always stated in terms of the population parameter, not the sample parameter. Symbolically, we state p equals 0.44, not p hat equals 0.44. We do not test a hypothesis about p hat because we know what its value is. The value of p hat is 0.52. So how do we find the p-value, the probability that our result of 52% is simply due to chance and nothing has happened or nothing has changed? The proportion of non-smokers in 1995 is still at the 1960 level of 44%. We will go back to the sampling distribution of p hat. Our sample size of 881 is large, so we know that sample proportions will be normally distributed. We could calculate the z-score corresponding to a sample proportion of 0.52, the one observed in our study, and then decide if this was an unusual z-score. The familiar formula for how to create a z-score for a proportion is on the slide. So substituting 0.52 for p hat and 0.44 for p, we arrive at a z-score of 4.78. Now that is almost 5 standard deviations above the mean. It is extremely unusual. In fact, if we use the standard normal calculator, we could determine and announce that the chance of arriving at a z-score this large is almost 0. And that is exactly what we will do on the next slide. And this probability is called the p-value. So after calculating a z-score based on our data and the hypothesized p-value, we need to find the probability of getting a z-value at least this extreme. This probability is called the p-value. Small p-values give evidence against the null hypothesis, whereas large p-values fail to give evidence against the null hypothesis. Suppose we find a p-value of a 0.01. What this means is there's only a 1% chance that a result was due to random fluctuation. It is likely something else is at work. It is important to note that we never actually prove a null hypothesis is wrong. Small p-values simply indicate that it is very unlikely that it is correct. Conversely, we never prove that a null hypothesis is correct. Large p-values simply tell us that it could be correct. Remember the analogy to the legal system. The jury is never 100% certain someone is guilty. There's just a lot of evidence that they are. And that they are never 100% certain that someone is innocent. There is simply not enough evidence to convict or state that they are guilty. Since p-values can range from minuscule to very large, researchers are often faced with a dilemma. Does a particular p-value give enough evidence to reject a null hypothesis? With a p-value of 1 in 1,000, there is little doubt that the null hypothesis is incorrect. But what about 1 in 50 or 1 in 10? It is because researchers have so often come up against this kind of question that several fixed values of p-values are commonly used.